Okay, welcome everyone to today's One World Mathematical Physics seminar. And it's our great pleasure to have Makiko Sasada, Sasada Makiko-san, that's the proper pronunciation. And as you know, Makiko has produced many beautiful things recently, but today she's gonna tell us about her recent result on the hydrodynamic limit. So Makiko, the floor is yours.
Okay, thank you very much for introduction, and also thank you very much for this opportunity to give this seminar. It's a really great pleasure for me, and especially thank you for Tasaki-san. So, okay, so now I want to start today's talk. So I will talk about recent result on the topological structure and the role of symmetry in the hydrodynamic limit of nongradient models. So, and this is joint work with Kenichi Banai in Keio University and also Yukio Kametani, also from Keio University. And actually they are algebraists and also geometry people. So I mean, so it's a kind of interdisciplinary joint work in different fields. Okay, so this is the plan of today's talk. And so in the first part, I want to explain what is the background of this research and also the motivation of our work. And then in the second part, I will tell you about our result. Actually, we have many, in some sense, many type of results. So I will not go into details, but I want to focus on main ideas or some essence, of our results. And in section 3, if time allows, so then I will go into details. But I think there are many overlaps between second part and third part. But I hope, it will help you understand more clearly what's going on. Okay, so let me start from the introduction. So this is very general background. So my talk is about some problem in non-equilibrium statistical mechanics. And so one of its goal is to derive macroscopic evolution equations from microscopic dynamics. And especially the derivation of diffusion equation from very simple microscopic models such as interacting random walks is still being studied very intensively, and there are still many interesting problems or questions, and especially in rigorous study. And one of the main idea of a rigorous method in this direction is known as hydrodynamic limit. So this is very rough image of a hydrodynamic limit. So, okay, so these are some microscopic models at scale, some scale n, and this second line should be some different scale, fine scale. And so as taking this size and actually space and time scaling is taking to infinity, then we should have some continuous thing. So at time 0.
May I ask a question?
Yes, of course.
So is there a notion of sliding scale involved in this hydrodynamic limit?
Mm-hmm.
Is there a notion of sliding scale?
Motion of a sliding scale.
I mean, renormalization group and sliding scale involved in this hydrodynamic limit?
Yeah. So so the scaling of time and space, and also the weight of each particle, for example. So is it clear? I hope.
I think that will be clear later.
Okay.
Yeah. So these red, for example, these red particles have some weight for each, but of course we want to keep the density is somehow converging in some sense, and then so this is at time 0 level, and then also as time goes to time evolves, of course each level of the scaling, we have some microscopic dynamics for this level or for this level. But finally, we hope to see something in continuous level. And in this final level, we hope to see something deterministic and also something which is continuous PDE. And yeah, that is some image, and more precisely, so mathematical statement of hydrodynamic limit is something like this. So we have some microscopic system at size n, and so we see some empirical distribution of some observable. So I will not make explicit here, but some some observable, and then it should be random. But and we consider dynamics of given microscopic models, and then we of course see some random distribution at time t. And so our assumption of the theorem is this. So as n goes to infinity, this at time 0 empirical distribution of some observable converts to something deterministic. So so microscopic profile. And then and the conclusion of the theorem is something like this. So here, this is a conclusion or consequence of theorem. So as n goes to infinity, then at time t, there's also some convergence in a good sense. As n goes to infinity, then we have something deterministic. And moreover, this macroscopic profile evolves according to some PDE. So, which is also given in the theorem. And for example, if there's only one macroscopic observable, then we will see one PDE. But if we have 2 or 3 or more multiple conserved quantities, then we should have a system of PDEs of these observables or macroscopic parameters. And for example, so this case, we should see the density of maybe red particles and the green particles and blue particles, for example. So we should see the system of PDEs of these densities. But the most simple case is actually if we have only one conserved quantity, and then we will see a kind of heat equation or some diffusion equation, or of course, also as a type of PDE. And so current status.
May I ask another question, if possible? So you're not necessarily assuming equilibrium state.
Okay, so of course we need many assumptions for this rigorous statement. So yeah, okay, maybe I will tell a bit more about this. So yeah, please wait a bit. So, okay. So yeah, and so far the current status and issues of hydrodynamic limits are as follows. So all previous works in the area of hydrodynamic limits are somehow case-by-case analysis of specific microscopic models. So specific means we choose some state space, and we choose a kind of type of interaction between particles, and also so kind of case-by-case analysis. And of course, there does exist a model-independent strategy of proof, and it's very powerful, and it is really nice. But still, there's no general theory in the general framework. So, and actually, there are many interesting models for which the hydrodynamic limit is expected to hold, but this has not yet been proved. So, and this the class is actually mainly called nongradient models. So there are many open problems in nongradient cases. And so universal structure in the analysis of nongradient models should be important if we consider, if we want to understand more, but it is not well understood, I think. So our goal, ambitious goal is to initiate a universal and general theory of hydrodynamic limit by introducing an appropriate framework of microscopic models. So yeah, we want to introduce really a general setting of microscopic models or definition, and we want to make clear what is the key for the non-gradient method works, or hydrodynamic limit is actually proven. And so formal derivation of hydrodynamic limit equation is done as follows. So maybe this part is will be the answer of the last question. But so we first need to characterize equilibrium measures. So we assume that this microscopic system has nice class of equilibrium measures, or maybe invariant measures. And then so the parameters of this rho, so the measures should be parameterized by some rho, and so this may have so not only one parameter, but some parameters, say density of particles, or energy, or pressure, or maybe some parameters. And typically, this rho I is the local density of some conserved quantity. So conserved means the total sum is conserved under the dynamics. And for example, the density of particles and the total number of particles are somehow related in this way. And then, so this first step is actually need to characterize what should be the macroscopic observables in the limiting equation. And once we know, then so we expect this type of PDEs since these rho I is related to conserved quantity. So this is just the equation of continuity, and GI current. And so I goes 1 to C. So if we have C conserved quantities, or C macroscopic parameters, and the most simple case is just C equal 1. And this number is continuous derivative. And then, so actually we want to derive this type of PDE, but so starting point is of course microscopic model. And so we have microscopic level similar equation. So Ci is now some conserved quantity, which is in a microscopic level. And so this is very formal notation, but we have a kind of this relation. And here the point is that this is now discrete derivative, so not a continuous derivative. And this operator is given by this. So tau of Ej is, okay, so we are in mind that, so we are working in this DD lattice, and then tau of Ej is actually so the shift operator of so E1, and this, so as a direction is tau E2 something, and the minus ID is just identity map. So this is a discrete derivative, and the Wi is called microscopic current. And of course, so this is a conserved quantity, so we have some type of this relation, and so this martingale term goes to 0. We can easily, usually we can prove that this goes to 0 as the scaling parameter goes to 0. So we can expect that this Wi should be something compares to GI.
Oh, but what are those microscopic current and like what is the domain of this microscopic current and the macroscopic current? Because I think the discrete operator is just bounded operator because it's bidimensional, but the Laplacian operator is unbounded, so we have to be careful about the domain. That's what I think. Okay, so yeah, of course there are many details, but so there are some kind of heuristic story. So sorry, but yeah, so we do not care about here the domain of functions, but yeah, so the idea is actually this is a discrete derivative, and this is continuous derivative, and by taking some scaling, so yeah, of course we more precisely this is scaled by 1 over n or something, and this converts to this continuous derivative. So, but In what sense?
Okay, so yeah. Yeah, if you, okay, maybe I can tell you if you want to know more precisely what this sense means, but I'm sorry, this talk focused on some more algebraic structure of this problem. So may I focus on this algebraic part today?
Okay, because I'm working on something very similar. So okay, let's talk later.
Okay, thank you. Yeah, so and then Euler scaling case, so if the system, microscopic system has some drift in some direction, then we expect that the limiting equation should be first order, and so the, yeah, and order, first order PDE, and we should take Euler scaling limit, means space and time are scaled 1 to 1. And then, so this Wi should converge to expected value of under this equilibrium measure, and we call this GI rows. And so, in good case, we can prove actually that this microscopic system converts to this GI row, and this PDE is obtained as a limiting equation. But if this current has average 0 for any row, then we should maybe we should think about this diffusive scaling, and this often happens if we have some symmetric system, for example, or mean zero microscopic system. In that case, so if we are lucky, then the condition called gradient condition holds. And what is gradient condition? So that is so Wij. So Wi is actually the vector valued current. So Wij is the jth direction current should be decomposed also in this way. So here again we see this discrete derivative. Oh, sorry, it doesn't work. Oh. Okay, so yeah, this discrete derivative again of some function. So here I don't say precisely, but maybe we should have some local function. But anyway, so if we have this explicit decomposition of this current with using this discrete derivative again, then we can again obtain under some nice, of course, condition. We take this, we can expect this will converge to the derivative, J prime. And also this part maybe converts to this expected value under the equilibrium. And so this idea is somehow, this is a kind of a rigorous method to guarantee the Boltzmann's idea to obtain this kind of this type of equation. And the difficult case and the more typical case is actually non-gradient case. And non-gradient means so the gradient condition does not hold. In that case, we need to prove decomposition called Varadhan's decomposition of closed forms. And of course, many of you may not know what they are. This is, but so the main idea of this decomposition is actually this microscopic current is decomposed in the sum of the discrete derivative of this conserved quantity, microscopic conserved quantity, times some coefficient, which should be a diffusion coefficient in the limit, and a negligible term. So that is a general structure we expect, and actually under good condition, we can prove this result. And then once we have this decomposition, then okay, this part again become a derivative. And this part is just rho I prime. So what we get is this diffusion equation, and this diffusion coefficient is actually the matrix which changes the basis of some Okay, so this Wij is one basis of some nice class of function, and actually this is other class of important functions, and so this has both have C times D dimension of function dimensions in here this linear space spanned by this Wij has C times D dimensional space, and also this class is has the same dimension, and so this D is understood as a change of basis in this finite dimensional space, and we can ignore other part in the scaling limit. And so this situation is typically expected, but of course to prove this rigorously is not easy, and we need to check case by case in some sense. And the most typical situation is the exclusion process on DD. In this case, the microscopic model is has a state space given by this just 2 point times DD, and this is called configuration space. And eta in this class, so is has so eta x represents a number of particles at x. So the typical configuration is something like this, and we consider microscopic model, which is given by given as a continuous time Markov process with a generator L. So, but so is this means it's not so difficult. It's just sorry. So with this rate Rxy, which is positive or 0 rate, particle at x moves to y. But if only if eta x equal 1 and this equals 1, so means eta y equals 0 case. Only if and only if there's one particle at x, and if there's no particle y, then this particle moves from here to x to y with this rate. So it's very simple model. And we always assume that, not always, but typically, assume that the translation invariance and also so locality of interaction. So means this Rxy, the jump rate is local function, and also the jump also happens in the finite range. So if x and y are too far, then this jump never occur. And also this is important, that non-degenerate. So this means so from any point x to y, after waiting some enough time, then this particle can reach somehow. So with a positive probability. So the state space is really connected on if the number of particles are same into configurations. So, and this means actually the density of particle rho characterize the equilibrium measure. So there is actually one parameter family of invariant measure, and there's no other conserved quantity. So this non-degeneracy is implies this. And so reversible or mean zero case expected hydrodynamic limit equation is this one, because we have only one conserved quantity. And so as I explained, we hope to see a diffusion equation. And so rigorous results. So if this is symmetric and simple, so simple means this Rxy jump rate is does not depend on eta, but it's just constant, only depends on x and y. In this case, actually the Ij is again does not depend on rho, and so this equation is proved rigorously. And here not necessarily nearest neighbor, but and reversible and nearest neighbor case. So still, so reversible with respect to product Bernoulli measure case, Funaki and German Yao proved this rigorously, and also reversible with respect to non-product mixing condition case, Savarin and Yao proved this equation. And so they are non-gradient models, and so we only have diffusion variational formula for this diffusion equation, and this is not like this case, but anyway, we can get this result rigorously. And other typical microscopic models are something like this. So first, generalized exclusion process is the model on the with the state space given by this. So here, kappa is some finite number, integer, positive integer, and so now at each site x of ZD, we allow at most kappa particles in the same site, and we consider now this number 2 or 3 describes the number of particles at each site, and then so interaction is the typical interaction is something like this. So if we have 2 particles here and 2 particles here, and this particle can jump from here to here. So this is a bit typical, interaction of generalized exclusion process case. And also we can consider multicolor or species exclusion process with the same state space, but now we understand one represents some color of particle and 2 represent other color of this particle. And then, in this talk, actually, I want to consider only the case where any pair of particle can exchange their position. So blue and red exchange the position, and or green and so even, of course, empty site is also exchanged. So 0 implies empty. And the color and the species, I use 2 words because so color means all the rule of dynamics are same for all particles, but just we distinguish particles' colors. And I call species if the dynamics are really different between different particles. So different color particles. So, and there are typical models, and also there are many, actually not so many, but at least several specific models for which Radan's decomposition theorem is shown, and this almost means that the hydrodynamic limit is also shown. So, as already explained, so lattice gas models, so is actually the class of interacting random walks on the lattice and the exclusion process or generalized exclusion process, or at least multicolor case. And but so here I mean not all. So the decomposition is a bit different because this case the model studied does not allow the exchange between different colors. But anyway, so there are some results on this. And also we'll discuss with energy. And also continuous type model, there are some results. Also Ginsburg-Landau, which is the original result by Radan, and some stochastic energy conserving model or system of oscillators plus noise, which is actually my result with Stefano. And but the important remark is for all models, the lattice is ZD. So that is first somehow the restriction of all studies, known studies. And interaction is actually nearest neighbor. And so this point is some, I understand there's some discussion, but the existing proof, if we read carefully the proof, then actually we use this condition at one point in the proof. So in the existing proof. So this was actually crucial. And also stationary measures are product except for the exclusion process result by Vardan and Yao. And this is the only result for not product case for Vardan's decomposition theorem. So yeah, there are still some restrictions. And so there are many interesting open problems, at least before our work. And so the multi-species case, so this is first not color case, and the species, so different dynamics case, or so energy Ginsburg-Landau kind of model, which is obtained from mesoscopic model. as a mesoscopic model from some deterministic model. So this is physically very interesting, I think. And in this case, a spectral gap is known. So this is only for expert, but even spectral gap is known, still it's not straightforward to prove the balance result. And also there's similar model. So this state space is R plus, and so this give us some difficulty actually. And also
is the spectral gap something like the gap between the lowest energy state and the first excited state?
Yes, and so we actually in the proof we need a very sharp estimate of this type of gap estimate in terms of the size of the system n, so system size n, and so but there are some technical point, but so the order of the gap is very important.
But you're speaking about the spectral gap of generator of the
yes, sorry,
dynamics,
yes,
right?
generator.
So it's not the energy, it's the generator.
Yes, generator. Yes, thank you. Yes, generator.
I think generator is the Hamiltonian and its eigenvalues are energy. That's what I think.
No, this model is not a quantum type system, so it's not. We cannot say in this way generally. So we consider more general models like.
So you mean the generator is not essentially self-adjoint or even Hermitian? That's what you mean?
No. In this talk, I'm I'm focused on the case with a generator which is a self-adjoint. Yeah.
Then I think it can be interpreted as Hamiltonian because but that's a different story. So okay. But anyway, it's not essential. Let's go on. Yeah.
Okay. Okay. So maybe we can discuss later. So okay. So there are some specific models which are not still have some difficulty, and also there's some more general extension. So which we expect to have, like finite range interaction case, not nearest neighbor case. So nearest neighbor means the jump is allowed only between nearest neighbor edges in ZD, but by the way. Or also we want to generalize this result to crystal lattice and such as hexagonal lattice or diamond lattice. And this difficulty comes from this heuristics in my first part. Maybe you can imagine that we get a discrete derivative in the very beginning. Okay, maybe I can go here. So this discrete derivative here, even at this very beginning, because we working on this ZD. So if we work on the hexagonal lattice, for example, we do not have this one already. So we need some different expression already, and we need some other technique to understand this hexagonal lattice, for example. And so, also again, this part is not clear what we should have. So, and the current is also again, current is not does not have this dimension in some sense. So the dimension of the space and the dimension or number of currents is not same anymore. So for hexagonal lattice, for example. So this is one of my motivation. So how we should understand this part. And of course, if we can generalize the result to non-stationary, non-product case, then it is really interesting, but this is out of scope of my talk so far. So at least our result applies a multi-species exclusion process case, and also a finite range interaction case, and also models on general crystal lattice, such as hexagonal lattice, diamond lattice, so on. So that is our result somehow. Okay, so now I want to explain what was the key and what is our general framework, and so what was new in our theory. So first, so I say intentionally, I say this is one result that we introduced framework of microscopic models. So, and now we consider this framework. So microscopic models are defined by some geometric or spatial data and also stochastic or temporal data. So that is one key idea, that we separate the information of microscopic model in the geometric one and the stochastic one. And geometric data are constructed from the triple S and phi and chi. And now S is a local state space, so what we call, and for the exclusion case, maybe this is, so it could become clear. So the exclusion case, S is just 0, 1, so just 1 point state space. And then next, local interaction is given by a map with on this S2 to S times S to S times S. And for example, exclusion case, it's just the exchange of observable. So this represents the interaction between two adjacent vertices. So what happens between two sides? And so in this model, we only consider two-side interaction. But the important point is we do not care the speed of interaction. So we only have here the information of what kind of transition happens if we have some interaction. And also there another input, which is underlying spatial space, which is a graph. So, and here the typical case is just ZD and ED. So ED is a typical edge, nearest neighbor edges of ZD, but more generally, we can consider, for example, ZD and EDR. So here EDR is just the nearest, so the pair in such that the distance is less than R, for example. And so here underlying spatial graph represents the vertex set and also the interaction, interacting pairs or something underlying space. So where we can see a direct interaction. And so stochastic data is actually speed of local interaction. So each interaction happens with some speed, and so in, for example, the exclusion case, so this is RE. So this is RXY. So it's a set of local functions. So we need all the information of the speed of our local function rate. But and this, of course, will give us some class of equilibrium measures. So the equilibrium measures are also stochastic data, but actually this is not a real input, but kind of a consequence or information obtained from the rate RE. So, and so far we don't have any symmetry data. So there are no homogeneity of the space, but so we also
equilibrium measure. Do you require like some property like ergodicity?
Yes. So yeah, of course, to prove the main statement, we need usually some nice ergodicity. Yes, and so we have a symmetry. Also, there's no input, no information from microscopic model itself, but usually we also have some symmetry in this dynamics, and so we consider as a group G, which is called symmetry data of the model, and if so G acting on this underlying graph, in this case ZD or hexagonal lattice, or yeah, we can consider a graph, but and typically we have some symmetry of the graph, and so this symmetry for the underlying graph implies some symmetry also in the dynamics. But actually, this is somehow additional information. Okay, and then so my main message is actually this geometric data has many information already. So even we do not know what is stochastic data of the model, still we can get many information of the model, and we can understand what kind of a decomposition should appear, or also and the symmetry data and so geometric data are enough to understand this algebraic structure of the composition. So first, so from topological data, or this 3 input, we can define the space of conserved quantities more generally in an abstract way, and which is a subspace of functions on this just one side function, a function on this one side state space. And so I will explain what is this later, but maybe you can imagine. So the sum of this function should be conserved under the dynamics, and that is a space of conserved quantities. And also this data, S and phi and chi, defines a big graph structure on this configuration space. So this is the main idea. So Sx is, so for example, again, exclusion case, 0, 1, and ZD is this space. And then this is the edge set of this graph. So this is a vertex set of this graph, and this is edge set. And what kind of edge exists here is actually eta and eta e. So and eta e is just obtained from eta, configuration eta, and we act in local interaction at edge E. So this is a set of all edges in this big, very big configuration space or graph. And from this graph structure, we can easily introduce.
Professor?
Yep.
I think it's better to call call this space because I recognize Sx as some kind of a symplectic manifold, and which is configuration space, and this graph structure as a tangent, some kind of a vector bundle on it, fiber bundle on it, so that it is called the phase space as far as I learned.
Phase space. Okay, yeah. We can also say that, I think.
Okay.
So yeah, anyway, so this is the edge set, and okay, so for graph, actually we have a natural graph cohomology, which is just given by the C0 is a function on all on vertices, and the C1 is functions on the edges. But and from there we can consider, of course, a cohomology theory of this graph, but this is actually useless for our work. And so this is very big space, and so we do not want to work on all functions on this configuration space. And usually we are interested in local functions in this space, but actually local functions are not enough to study shift invariant functions in somehow. So in the Baradin theory, we often see this kind of functions, which is just formally understood. So this is all shift of function f. F is some local function, but we consider all shift of this tau f and add this infinite sum, consider infinite sum. So this often happens in the non-gradient method theory, but so far we do not consider this as an existing object, but just a formal sum. But in our theory, actually, this is in this class uniform functions. And so unfortunately, I don't have time to explain what this class really means, but actually we can make sense of these functions, or also the conserved quantities like this total number of particles in this class. So they are all well defined in here. And we can also consider some uniform forms. So it's also a kind of generalization of one form on the graph. And so differential is just the usual one. So this gives, so if we have the f of, so h is actually eta and eta e, the pair of eta and eta e. And so this is just given by the difference of f eta e and f eta. So this appears very naturally in the generator. So this differential operator is very useful in our study. And also we introduce closed form or exact form in usual sense, but okay, so maybe closed, we need some definition, but and then homology is defined by the kernel of H0, and H1 is the quotient over T1 over this exact form. And this is very abstract and algebraic, but so under some assumption, we can prove that this H0, this class actually catch the information of conserved quantities. So they are isomorphic. And so conserved quantities, it actually should be macroscopic parameters of our equation. And so this is characterized by geometric data. But of course, it's very natural and clear in the physical sense, or maybe point of view, or so intuitively. But the point is we can catch this information or abstract notion of conserved quantities in terms of homology, like a homology. And so there are two assumptions and type of assumptions. And under assumption 1, we can prove this result, and also under assumption 2, we can prove the same result. And I want to explain briefly what this assumption means. And this is a non-degenerate condition. So ergodicity may be related to ergodicity, so exclusion case, a non-degenerate condition. So, and this condition is again we can formulate in algebraic way, so without any speed information. And this is a bit technical one, maybe seems technical condition, but anyway, ED is okay for D bigger than or equal to 2, but for D equal 1 case, it's not true. So this D equal 1 case, only we can say that this is weakly transferable. And so actually this is dimension is has essential difference, and so we can construct a counterexample for this result, so especially H1 result for D equal 1 case with 2 or more conserved quantities. So they have essentially different structure as a graph. Okay, and this case, so
what is the meaning of the word transferable?
yes. So this is of course important. But okay, so the very rough idea is if we have this graph, and if we take some ball, and still the complement is connected. So that is almost a transferable. More precisely, we call this a strongly transferable, but we talk about the connectivity after we take some ball, some size of ball. So from DD, so if we take any ball, any finite size ball, still the complement is still connected. But the Z case, of course, it's not. So this becomes two connected components. This has two connected components. So this is the difference somehow. Okay. So, but if I have time, I wanted to explain more, but maybe I don't have time. So sorry. But maybe important message is so first, this graph, the infinity of this graph is the key. So if we have finite graph, then we do not have this result. So we cannot catch the information of conserved quantity. And this is why, because So total number of particles is a uniform function, or so it's in this class, but its square is not. So we can actually distinguish the total number of particles and its square. So even both are, of course, conserved under the dynamics, still this algebraic structure distinguishes these two numbers or two observables. And so then actually, if we have this, then so this second result is actually a simple corollary from this result. So here we do not use any symmetry data, but now if we also have a symmetry data, or so if some group G acts freely on this locale is sorry, is it graph, underlying graph, then this action easily induce also the action on functions or forms on this bigger graph, this graph. So the action is naturally induced, and then we can consider G invariant exact forms or G invariant closed forms. And if we consider now G invariant part of cohomology, then this first cohomology becomes is expressed in terms of just the first group cohomology of G. So here we only need or we only see the information of the group action G. So this quotient is somehow independent from the detailed structure of the graph, or so S or phi or such thing. But we only so this quotient only catches the group homology of this group G. But the coefficient is in this class conserved. And this is why, because we have this result. So, and this is the result, and if we have these two results, then this third result is actually a very simple corollary from algebraic discussion. And so, so if G is actually ZD, then we have this decomposition. And so maybe you cannot see what why this is important for, but so this closed form relate to a microscopic current, closely related, not exactly itself, but it's related to microscopic current, and this exact form is a negligible part. So, and remaining part is actually related to a diffusion coefficient. So so now we can say that at least the size of diffusion matrix is characterized by this symmetry data and also geometric data. So we do not need any stochastic data or stochastic information. And also this type of decomposition is actually can be proved without any spectral gap estimate or any information of invariant measure and so on. So this is independent from this information, and we can directly prove this decomposition result only with geometric data and symmetric data. And finally, so what is about variational formula or Bardant's decomposition theorem is understood in this framework. And this is actually the completion of this form is the invariant uniform exact forms is class appeared in Bardant's decomposition, and also set of invariant to closed form is also again the completion. Yeah.
Completion with respect to which?
Okay, completion with respect to this inner product using this stochastic data. So maybe some people who already who know about this nongradient method will maybe can imagine, but so we introduce some kind of inner product for this one form. So maybe this is too too rough, I think, but E0 or so E0 is actually given by E over G. So the edge set over the group action. And so omega and omega prime are one forms. Then we can introduce in a product with this weight, RE is the local function, the jump rate, and the new rho is the equilibrium measure. So this introduced in a product in this tangent bundle somehow. And this is analogy to Riemannian metric for Riemannian manifold. So this is really the same situation. So if we have a manifold, then we have smooth cohomology, and also we have some derivation cohomology. But if we have some Riemannian metric information, which is really a counterpart of stochastic data, then we can introduce the inner product in this tangent space of one forms as a Riemannian case. And then, yeah, we have L2 forms. So this inside is kind of smooth forms, and then we have L2 forms as its completion. And this again have the same decomposition. But of course, here we need many assumptions compared to here. So this part we need only a very few assumptions. But in this part, so far we need many assumptions, like S is a finite set. So this is really strong. But so far our construction is only for discrete type model, and we hope to extend this to continuous type model. But yeah, so far we can only work on this S is finite case, and also G is a ZD case, so very specific, but still it covers many important cases, and especially have multiple conserved cases covered. And of course, here we need a spectral gap estimate. So for expert, so far we do not have any idea to skip a spectral gap estimate, but so essentially we only need somehow this condition. And sorry, and of course this includes essential assumptions, includes also mu new rho is a product. So this is also so far very important for us. But yeah, I hope also yeah, the new rho important in the spectral gap estimate. And yep. But essentially they are just needed assumption. And then so we can
may I ask, so for example, we can apply the theorem to 4-dimensional Euclidean or Minkowski space with the Poincare or Euclidean group as the symmetrical, right? Which is continuum. And which is continuum.
So yeah, so far yes, S is not continuous, and yeah, so the situation is very different, I think. Yeah.
Okay.
So and maybe from our general framework, we can also say something, a new interpretation of the macroscopic diffusion matrix. So now this decomposition is a kind of a topological version decomposition, because this decomposition itself, and also we can actually get explicit decomposition, some canonical decomposition in terms of topological information. So there is one canonical decomposition which is given by Varadon's usual classical decomposition. And also, of course, we always have this orthogonal decomposition if we have in a product. And so diffusion matrix can be understood as a transition matrix of two different decompositions, so topological one and orthogonal one. And this relation also appears in some as a period matrix in algebraic geometry story. So maybe there's some interesting connection between these two stories. Okay, so yeah, actually I planned.
Yeah,
I will stop.
I'm afraid that it's already Wednesday for two of us.
Yes. So I don't want to actually explain here. So I just wanted to, yeah, if I have time, I want to go into detail. But sorry, I want to just explain the future work and the ongoing work. Oh, sorry, what happened here? Yeah, so
or you can talk about
this
the
is the final
best
slide.
examples. Yeah. Oh, okay.
Um,
Yeah, but you can talk about the best examples that you're to
Okay,
which
okay,
your
so-
general theory apply, right?
Okay, so maybe our result applies so hexagonal lattice or transfer. Okay, hexagonal lattice or yeah, triangular lattice and so on. And okay, so maybe so any let me see. So this smart color or species exclusion is also allowed in our result. And so I'm now working on this specific multi-species exclusion case. I'm writing a paper for hydrodynamic limit because the result itself is only for decomposition, and this is an essential part for hydrodynamic limit. But so now I will now I'm summarizing this, and if the limiting PDE is a system, we have some still difficulty, but I'm working on this part. So this is a ongoing work. So diffusion variational formula is given by this general form, and here Onsaga reciprocity, I think so, is actually appears here. So we have this very general structure, and we hope some extension of other models on non-product case, but this part is still, this part is difficult, but I think this part is not so difficult. So thank you very much. I stop here.
Thank you, Makiko, for exciting talk about, really hot topic, ongoing topic. So I believe there are many questions. So anybody?
You said there was a natural decomposition, like canonical decomposition. That's what you mentioned. And in what sense is it canonical? Like, is there categorical argument involved in so that it makes the decomposition canonical in the sense of functors and categories?
This actually, this is a canonical decomposition. So maybe I can, thank you for the question. So if we have a closed form, then explicit decomposition is given by this, and this part is exact form because this part is actually a sum of shift. So it's an exact form part, and this part is a non-exact part. So this is a quotient part, and so C is a conserved quantity. So if we fix some basis of conserved quantities, so usually maybe physicists usually start from some specific choice of the basis of conserved quantities, like energy and this density of red particle or density of blue particle. But of course, mathematically, we can use a different basis of conserved quantities. So once we fix this, and then also we fix the basis of this group action, then, and also we fix fundamental domain of this x0, so the fundamental domain of x over g, then we have this explicit decomposition somehow, and this is a canonical decomposition in terms of this choice of basis. And
what I know is that if a choice of basis is involved, then it's not really canonical. So something that is canonical should be basis independent, like quality independent. That's what I meant.
I see. Yes, I mean canonical in the sense that this decomposition is independent from the choice of stochastic data. So I mean, there's no information of measures. So this decomposition is really independent from any measure. So so this is one way to decompose closed form into exact part and other part. But we can also have a orthogonal decomposition once we have information of measures. So, and this relation, this exchange of the basis or decomposition is a diffusion matrix. So that is what I want to say. So this decomposition, first decomposition is nothing to do with measure. Yeah.
I see.
Okay,
thank you.
Okay, so there are questions from Stefano and Herbert. So please, Stefano, please.
Yes, about the Gies-Brandau energy model, that is apply as long as spectral cap even though it's not finite state space.
Yeah. So far, yes, this structure does not work for Ginsburg-Landau case because S is not. But I think this generalization is actually possible. So not hard part, but the main difficulty is actually we need to take care of the class of functions. So here I introduce the nice class of functions called uniform function. But here we do not need to care about the regularity of function. But for continuous case, actually, we need to take care for the forms and functions of the regularity and what class should be. And but I think it's possible. So I need time, but I hope. But this more, theory is so far or discrete.
Okay, thank you, Makiko.
Yeah,
Okay,
thank
Herbert.
you.
Yeah, so thank you for interesting talk, but I wonder what in this more general framework, I mean, what happens to the Green-Kubo formula? I mean, it's still there somewhere hidden or simply not very useful or specific for hypercubic lattices, or what happens to the Green-Kubo formula?
Green-Kubo formula. Okay, yeah, so Green-Kubo formula is already, I think, so in this equation, so variational formula, it will tell you something, or so this, let me see.
You said Onsager is there. Is that correct?
Onsager, yes. So this part is some variance matrix for so this conserved quantities. So this is symmetric, and this part is also symmetric, positive. So D is not anymore symmetric, but we have so this decomposition, and so this part is variance of this chi-rho is actually given by variance. See.
So you can re-express this in terms of integral over carbon-carbon correlations.
That is a good question. So current, now I think current is not for I think so for each edge we have a current in this here and here and here, but the WE1 and E2 and E3, but they are not independent anymore. So we need to define W1 and W2 from these three currents somehow. And so this is already not, I think, not canonical. So of course we can choose so sigma, sigma 1 and sigma 2, so the direction, for example. And then we can define what they are, and then maybe that I didn't think carefully, but it's a good interesting point, I think.
Very interesting.
Very much, yes. No, I think the example is very useful. I mean, the hexagonal lattice, I mean, you have to really think hard how to do it actually, right? I mean,
Okay, so Yao, please.
Yes. So I'm curious. So suppose you want to prove this, and I mean, usually in Vardan's case, you take a limit of this. I think it's closed form, and so now it becomes suppose you have two conserved quantities. And can you give me some ideas of why two conserved quantities to run this argument with essential difficulties?
Two conserved quantities case, why?
Yes. Why the two conservative quantities case are different from the original Vardan's case, and where is the main input you have to worry?
I see. Yes, actually, thank you very much for your very nice question. So the most difficult part to make this in general is actually so finally if we can prove that the spectral gap, then of course we can construct from some closed form, some approximating sequence of exact forms, and some boundary term, and the boundary term should converge to something. But finally, what is the limit of this boundary term is very mystery so far. And yeah, so that is a point of my talk. It should be. So thank you very much. So the limit of boundary term is calculated by case by case, and so we see finally always we see this form, this specific form, but we didn't know why. So and if we have many conserved quantities, then the dimension becomes bigger and bigger. And so far we always check all the algebraic equation which boundary terms satisfy, and we calculate this equation somehow by hand. We obtained this by hand. So if we have only one conserved quantity, then this means we should have the algebraic equation,
Yes.
because this is the measure. But if we have two, then there's 2D and 3, and we have 3D, and so and we have many equations for boundary terms, and some of them are not linearly independent. So we just carefully count, and so on and so on. So, and this part is always model dependent, and there was no model independent strategy for this. So to calculate this boundary term. So yeah, thank you. Yes, actually, this was my also one of the important original motivations. So why we always have this form universally, and from original proof, I couldn't see the reason why we always have this term. So yeah, and the algebraic argument really give us the reason. So now our main result for L2 version is just we prove a boundary term should have some limit, and this limit is local closed form. So that is the point. And once we can prove that this limit is local closed form, then so this is not this does not have infinite support, then we can use the original result so without measure. So yeah, so we can reduce the problem to the decomposition for this this result without measure. So yeah, thank you very much. I should explain this part more. Yeah.
Thanks a lot. I know your time is limited, so thanks a lot. Thank you.
Very good. Any other questions or comments? Okay, if not, let's thank Makiko again.
Thank you.
Thank you.